we're going to look at mean, variance, standard deviation, and expectation, and that's the part that's going to be a little bit different from a probability distribution, which is what we did in 5.1, and I'm going to reference that particular probability distribution that we went through with the getting three tails in this lesson. Okay. There are two formulas that you really need to know. One is the formula for mean, which is going to be a new formula for you today, not hard at all. And then the formula for variance and the relationship between variance and standard deviation, and then we'll talk about expectation at the end. Okay. So we're going to talk about first finding the mean from a probability distribution. Okay. And what you really do to do that. You're going to take the outcome, whatever that outcome is, and yesterday it was 0, 1, 2, or 3, the number of ways that you could get three, or getting tails. So you could get 0 tails, 1 tail, 2 tails, 3 tails. And then those probabilities, those outcomes, you're going to multiply the probabilities, and you're going to add those up. So it's going to be the sum of the product of the outcome and its probability. Add those up, that's how you find the mean from a probability distribution. Okay, so this is what I referenced. This was in 5.1. Okay, so this was that probability distribution. Knowing you flip a coin 3 times. If you get 0 tails, there's 1 out of 8 ways. The probability is 1 out of 8 to get that. There's 1 way to get no tails. That's 3 heads. Okay. There's 3 different ways to get 1 tail, so the probability is 3/8. There's 3 different ways to get 2 tails, so that probability is 3/8. And there's 1 way to get 3 tails. That's 1 out of 8. Okay, so that's that probability distribution from 5.1. So what you're going to do to find the mean is multiply that, multiply that, multiply that, multiply that, and then add them up. Okay? So go ahead and do that. Again, remember the lowercase mu, Greek letter mu, stands for mean. Okay, so then multiply those all together and add them up. And we want a decimal. Okay, we're going to use decimals when we go through these. So at first, I'm going to do it with fractions. They're all eighths. So at first, 12 over 8, that converts to 0.5 or 1.5. Okay. So that's the mean. And if you think about it, in terms of this probability, we expect to get, which I understand that this doesn't necessarily make sense. How can you get 1.5 tails? You can't get a half a tail. But if you notice the distribution, it's sort of equal on this side in terms of probability, equal on this side. So that's why the mean is going to be in between 1 and 2. Okay, it ends up being right in the middle there. Now, we're going to need the mean in order to find the variation and the standard deviation. So every time it asks you to find variation, the variance, or if it asks you to find the standard deviation, you have to calculate the mean if it's not given to you. So this might not be, there might not be a problem that says calculate the mean. It might say find the standard deviation. But in order to find the standard deviation, you need the mean, so you'll have to do this calculation. Okay? Keep that in mind. Questions so far? All right, talk about, also, before we get there, if you're using your book at all and you want to look, this means the sum of the outcome times its probability. This is the actual formula for the mean. Obviously, we talked about what to do, and here it's written out in words, but here's the mathematical symbolism for it. Remember, the sigma means sum of, and x is the outcome, p of x is the probability of that outcome. So that's the notation that you might see in the book if you decide to look in the book for it at all. Okay? Bless you. All right, let's move on to variance and standard deviation. Okay, what's the relationship again? Remind me, the relationship between variance and standard deviation? Square root and square, which one is which?
Variance is for standard deviation squared.
Variance is standard deviation squared, which means the standard deviation is?
Square root of variance.
Square root of the variance. So, and this tells us how spread out the data is. That's what those values are useful for. And just a quick little reminder, there's the relationship. What we're going to do when we have the probability distributions, we are going to find the variance. Then we're going to use the variance to find the standard deviation. Okay, so we're gonna do this, then we're going to square root it to get the standard deviation. Here's what the formula is. I think that's the next thing. Yep. Here's the for variance. Okay. So remember, sigma squared is variance, and I'm going to talk through what all these other parts mean. So there's some similarities between the mean formula and the variance formula, but there are also some differences. Okay. First off, the glaring difference over here is you're subtracting the mean squared at the end. You're going to find the sum of all of this, and I'll talk about what this is in a second. Sum of all of this. And then at the end, you subtract off the mean squared. So in order to calculate the variance, which was what I was saying before, you still have to have the mean. Okay? Notice the difference between what we had for the mean and this part of the variance. It's the sum of the outcome squared times the probability. So in the mean, it was just the outcome times the probability. For variance, we take the outcome squared times the probability, add all of those up, and then subtract the mean squared. That's the difference. And then the standard deviation is just the square root of that. Okay, so that's the only difference. We're going to actually find this, find that value, then we're going to square root that to get the standard deviation. No, this is something you're going to have to know how to do. Yeah. And we're on the next slide. We'll go through and find the variance and standard deviation for that same probability distribution that we're looking at with the three, or getting tails, flipping coin 3 times. We'll go through and actually do that calculation so we can practice it. No, there's no reason to memorize this formula at all because it's just the square root of this. Right? So you need to know this. But once you work through it, we're going to work through it in homework today and over the weekend. We're going to work through it again on Tuesday. You're going to have it down. All right, it's not that complicated. So when you're writing this over here, I would just copy paste and do the square root of it all. Okay. Let's look at how to calculate variance and standard deviation for that distribution. So again, we're still talking about flipping a coin 3 times. How many tails can you get? So instead, here's the only difference again. So to find the variance, because that's where we're going to start. Okay, we're just going to, you have to square what's in blue before you multiply it by the probability, still add them up, then subtract the mean squared. Okay. And again, formulas, that's just copy pasted, and mean was 1.5, which we had already calculated. So go ahead and try to find the variance. Again, square the outcomes, multiply them by the probabilities, add those up, subtract the mean squared. Try that. Here's the formula. Here's what you should have had. Okay. So again, I square everything in blue, multiply it by the probability, subtract off the mean squared. Okay. How many had that set up correctly? Okay. Good. Obviously, with 0, it's helpful because this just goes away. With 1, it's just 3/8. You can plug this all in your calculator too, pretty easily. This all equals sigma squared, which is variance. So that is 0.75, or you could have listed it as 0.8. What's going to be really important on your quiz and on your test, or especially on your quiz, because the quiz won't be multiple choice. If you choose to round this to 0.8, because in order to find the standard deviation, you're just square rooting it, right? So I need to see that you're square rooting 0.8 instead of 0.75. In reality, since this one comes out even, I would prefer that you not round it, since it comes out, all right? To find the standard deviation, what you have to do is take the square root of that, which come out nice, and so I do want you to round that. That is 0.9, okay? Would we say that the data is very spread out or very close together?
Pretty close together.
I mean, these numbers are not big, right? They're small numbers. So we would expect those numbers to be close together, which they are, okay? How many have those two? So, this is on page 263 in your book, or you can take a picture of it, and I will talk through what all's going on here, because this is kind of a complicated problem. Finding the variance and standard deviation for this distribution is not that hard, but answering the question, should the station consider getting more phone lines, that's a little more nuanced, so we'll get into that. So get that situated. Actually, go ahead and do that. Find the variance and standard deviation first, and then we'll talk about what to do with that. In order to find the variance, you first have to find the mean. Understand that. So we have to find the mean first, which means you have to multiply these, add them, and you get 1.6. Okay? Then to find the variance, we have to square these, multiply, then add them. That should have gotten you 1.2. The square root of that is the standard deviation, which is 1.1. Now, here's how I'm going to use all of this information to come up with answering the question. First off, what's going on in this problem is just this radio station. People call in, they have 4 lines. They give you the probability of this many people getting through. Okay? The probability of all 4 people getting through is pretty low. 3 people getting through with 4 lines, and 2 is about the same. 1 person getting through, of course, is the highest probability. Right? 1 person can get through, but 2 or 3 or 4 at the same time, that's a little tougher, but it can be done. What we're trying to figure out is whether or not they need more phone lines than 4. And so what we're going to do with this information is we're going to try to see where most of the data is going to lie. And that's why we use the standard deviation. Because how far away stuff is from the mean, what percentage of the data is so far away from the mean, the more of it is less than 4, the better off we are with 4 phone lines. If most of the data is bigger than 4, because obviously less than 0 is a negative number, you can't have negative phone lines. But if most of the data is bigger than 4, then we need more phone lines. So here's how we use the relationship between the standard deviation and the mean. If you remember, when we looked at Chebyshev's theorem and standard deviation, that when we were 2 standard deviations away from the mean, what was the minimum percentage that was of the data that could be within 2 standard deviations?
68%.
That's for normal distribution. This is not a normal distribution. We don't know what it is. So the minimum percentage for 2 standard deviations was at least 75% of the data, and that was 1 minus 1 over 2 squared. Okay? So here's what this means. Most of the data, at least 75%, could be more, most of the data within 2 standard deviations of the mean, if most of the data is below 4 or less, then we're in good shape. If most of the data falls higher than 4, then we need another phone line. Okay? So if 1 standard deviation is 1.1, what's 2 standard deviations? 2.2. So take that and add it to the mean and find out if that is bigger than 4. Okay, and if I calculation, I take the mean, add 2 standard deviations, because if I subtract it, I get a negative number, right? If I subtract 1.6 minus 2.2 is negative phone lines, that doesn't make sense. Obviously, you're not going to have a radio station have people to call in and have no phone lines. That doesn't make any sense. Okay, so what this means is that at least 75% of the data is in between a negative number and 3.8 phone lines, which means most of the time 4 phone lines is enough, because this number is less than that. If this number would have been bigger than 4, then we probably would say, yeah, we need more phone lines. But because most of the time, and again, it's at least 75, it could be bigger. Most of the time we're under 4 phone lines, or equal to 4 phone lines, we're in good shape. We don't need more phone lines here, okay? So we're going to connect what we've done before with the percentage of values away from the mean. They shouldn't need more phone lines because this number ends up being less than the number of phone lines that they already have. So we're in good shape there, okay? we need to get into expected value. And I'm going to give you two kind of formulas for that, which aren't hard. First, that's what we're talking about, is expected value. Here's the first formula. The probability of gain minus the initial investment. And the way that we calculate the probability of gain is actually just take the mean. So maybe it's better if I line up the minus signs. Is that better? So these two things are basically the same. And that's why this is included in this section. Because we're going to take the mean from, we're not going to actually have a probability distribution per se, but we're going to find the mean as if it was a probability distribution. And so that's what our expected value ends up being. And we'll go through two problems to make sure you follow how to do that. Here's the problem. So if you want to take a picture of that, you can, and we'll talk about how to calculate it. So in this case, we're talking about some kind of raffle where they're raffling off a color TV. And the value of that TV is $350. Okay? So if we win a $350 value. Okay? What is the probability of actually winning if you buy one ticket?
1 in 1,000.
1 out of 1,000. Okay? But what I have to do is actually calculate the mean, because the value that I expect to win is 350. So I take that probability times that 350, and then I subtract my investment. Well, what's my investment? $1. So when I find my expected value, what I do is take the probability. So this part's like the mean. In this case, there's only one outcome, right? The probability of that is 1 out of 1,000. The outcome is winning a $350 TV. Okay? And then I subtract off my investment. Now, if there's 1,000 tickets and I buy one of them, do we think we're going to win? No. The probability is very low of winning, which means we technically should lose our investment. So our expected value we would have, if you lose, we expect that to be negative. Okay? So in this case, what I'm going to do is do this calculation, and what we expect over the long haul is you're going to lose 65 cents, which doesn't really make sense, right? You lost $1. But because of that one little chance of winning, that increases your loss from, I should say it decreases your loss. Instead of losing a whole dollar, over time you would lose 65 cents, because eventually you're going to win. And that 350 balances out that if you bought 1,000 tickets, right? It's the same kind of way of looking at it that way. If you bought 1,000 tickets to guarantee that you win,
You still
lose $650. So for each dollar you spend, you really lose 65 cents on the dollar. Okay? That's what expected value is about. Okay. Let's look at another problem that's similar. But now there's 4 prizes. And you could possibly win twice, because we put the ticket back in. Your ticket could win twice. Why are they telling you this? What does that tell you about the probability each time?
It's high. Right.
It's the same.
It's the same, exactly. So because they put your ticket back in, you have the same number of tickets in the basket, if you will, that they're drawing from each time. So the probability of winning each time remains the same. So what is the probability of winning in this case? How many tickets did they buy?
Oh,
2.
2. So what's the probability of winning?
1 in 500.
1 in 500 or 2 out of 1,000, right? 2 out of 1,000, obviously we could reduce that. So that's still not great. Do we expect to win out of 2 out of 1,000? No, we're probably still not going to win. Might not be as bad as the other situation, since we doubled the probability of winning. But now what am I going to multiply 2 out of 1,000 by? Yes, you do have to do it for each one. You have to do it for 100, because there's a 2 out of 1,000 chance of winning $100. Then the ticket goes back in. Now you have a 2 out of 1,000 chance of winning 50. So now try to solve this the same way we did the last one, except instead of there only being one outcome, there's 4 outcomes. Right, since you buy 2 tickets, you subtract $2, because it's $1 a ticket. So, here's my setup, okay, the probability times each outcome, subtract the $2, cause that's your investment, and we expect to lose $1.63 over the long haul, alright? So it's a little bit better, right? The first one was, we lost
No, it's actually worse.
65 cents, well, cause we invested $2, but, so we gained 37 cents back. The other case, we gained 35 cents back. Right, cause if my investment was $2, the difference is 37 cents, the other one, the investment was $1, and the loss was 65 cents. It's still not great, right? And that's the point here. If your chances of winning are 1 out of 1,000, 0.1%, doubling that to 0.2% is not a huge gain. It's a little bit of a gain, and we see a little bit of a gain, but not a lot of gain, okay? So that's when people go, oh man, the Powerball's up to $1 billion, I'm gonna buy 10 tickets. Yeah, your chances of winning are still really, really bad.
You wanna buy a lot of
Okay.
tickets tonight.